Hi everyone, thanks for tuning in. In this video, we are going to present about nuclear fusion. To start our presentation video, I would like to introduce our group members. There are 5 members in this group, including me. Hi, my name is CEASTER Carlos Lee, and the others are Kira Nicole, Muhammad Irfan, Nur Natasha Irwayo, and NURUL ERNIERA. So, what is nuclear fusion? Nuclear fusion is the process by which two light atomic nuclei combine to form a single heavier one while releasing a massive amount of energy. So, what are the importance of nuclear fusion? One of the greatest advantages of nuclear fusion is its potential to provide a nearly limitless supply of energy. Fusion fuels such as deuterium, that comes from water, and tritium, which can be bred from lithium, is abundant and widely available around the world. Next, nuclear fusion is clean and green. Nuclear fusion is an environmentally friendly energy source. It produces no carbon emissions or other greenhouse gases, making it a powerful tool in the fight against climate change. Nuclear fusion also has no long-term nuclear waste. Unlike nuclear fission, fusion generates minimal radioactive waste, and what it does produce is typically short-lived, reducing the burden of waste management and storage. Nuclear fusion also inherent safety. Fusion is inherently safe. There is no risk of meltdown or catastrophic failure. If any disturbance occurs, the fusion reaction simply stops on its own, making it much safer than conventional nuclear power. Lastly, nuclear fusion supports energy security. Fusion can significantly reduce the world's dependence on fossil fuels and geopolitically sensitive energy sources. It can enhance energy independence and security. Next is methodology. There are 3 primary approaches scientists are using to achieve controlled nuclear fusion on Earth. One of the main approaches is magnetic confinement fusion (MCF). How does it work? In this method, superheated plasma, also called as an ionized gas, is contained within a toroidal, donut-shaped chamber using powerful magnetic fields. The goal is to keep the plasma hot and stable long enough for fusion reactions to occur. Common devices used for MCF is tokamak, for example ITER in France, and stellarator. Fuel used in MCF is typically a mixture of deuterium and tritium, and the goal is to achieve sustained high-temperature plasma confinement for energy production. Next is inertial confinement fusion (ICF). It works by tiny fuel pellets containing fusion fuel are stuck by intense laser or particle beams from all directions. This causes the pellet to rapidly compress and heat, triggering fusion in the core. The key facility is National Ignition Facility (NIF) in the USA. The goal is to achieve ignition, which is more energy out than in, through rapid, symmetrical compression and beating of the fuel. And lastly, emerging and alternative approaches. Emerging and alternative approaches are newer, innovative designs being explored by private companies and research groups. They often aim to be smaller, cheaper, or more efficient than traditional methods. Examples include compact fusion reactors, for example, by Commonwealth Fusion Systems, Tate Technologies, Z-pinch devices, field reverse configuration (FRCs), and magnetized target fusion. These approaches are still under development but show promise for faster commercialization of fusion energy. Despite its vast potential, nuclear fusion also faces several significant engineering challenges. First, nuclear fusion needs extreme conditions. Fusion reactions require temperatures exceeding 100 million degrees Celsius, that is much hotter than the core of the sun. So, creating and maintaining such extreme conditions on Earth is extremely difficult. Secondly, nuclear fusion also has plasma instability. The hot, charged plasma needed for fusion is inherently unstable. It tends to fluctuate and escape confinement, disrupting the fusion process and damaging containment systems. Third is energy balance. Most fusion experiments currently consume more energy than they produce. Although some have achieved brief moments of net energy gain, sustaining it continuously remains a major hurdle. Next is material durability. Fusion reactions release high-energy neutrons that bombard the reactor's inner walls. These materials must withstand extreme heat, radiation, and structural stress over long periods without degrading. And last but not least, Nuclear fusion requires high costs and long timelines. Fusion research and reactor construction require billions of dollars and decades of development. Commercial fusion energy remains years, if not decades away, depending on technological breakthroughs and investment.
NF importance. So NF offer clean, visually limitless and safe energy sources that could transform the global energy landscape. So this is the list of NF importance, where the first one is minimal radioactive waste, where fusion produce no longer leave radioactive waste. Unlike nuclear fission, its byproduct is helium and inert, where it is a non-toxic gas. Next, no greenhouse gases. Unlike fossil fuel, fusion does not emit carbon dioxide or other harmful pollutant, making it more powerful against climate change. Okay, next, low risk of meltdown. Fusion reactions are inherently safe, so if something goes wrong, the reaction simply stops. No chain reactions or meltdown risk. Okay, now we talk about example related. So the first one is suns and star, where fusion is the process that powers the suns and all stars. So in the sun's core, hydrogen nuclei fuse to form helium. So this causes releasing massive energy that reach Earth as sunlight. Okay, next is hydrogen bomb or H-bomb. So this is a destructive example of uncontrolled fusions, where in the H-bomb or hydrogen bomb, there is a deuterium and tritium nuclear fuse under extreme pressure and temperature. So when it explodes, it releasing enormous energy. Okay, the last example related is ITER, which is the full name is International Thermonuclear Experiment Reactor. You can see from the slide the reactor picture. So this is the world largest fusion experiment, where it aiming to demonstrate the feasibility of sustained fusions using magnetic confinement in a tokamak reactor.
Now we will talk about the applications of nuclear fusion as a sustainable energy source. Nuclear fusion involves the joining of light atomic nuclei, typically isotopes of hydrogen, such as deuterium and tritium, under extreme temperatures and pressures to form helium and a neutron, releasing massive energy in accordance with Einstein's equation E equals to mc squared. First off, the base load electricity generation. Fusion reactors can provide constant, reliable power, unlike solar and wind, which are intermittent. This makes fusion ideal for base load energy, which is the minimum power required by the grid at all times. Next, the hydrogen fuel production. Fusion reactors could be used to power high-temperature electrolysis or thermochemical cycles for splitting water into hydrogen, a key clean fuel for transportation and industry in the future hydrogen economy. Furthermore, we have waste reduction versus fission, where, unlike fission, fusion does not produce long-lived radioactive waste. This reduces environmental and political risks and simplifies waste management strategies. Last but not least for applications, the energy security. Fusion uses abundant fuel sources, such as deuterium from seawater and tritium brought from lithium. This ensures energy independence for many countries, reducing reliance on fossil fuels or geopolitically sensitive energy imports. Here are the recent studies related to our topic. Firstly, MIT Energy Initiative. A techno-economic modeling study by MIT's Energy Initiative and Plasma Science and Fusion Center found that if fusion power plants are cost-competitive and reliable, they could reduce decarbonization costs by trillions. Fusion is viewed as a crucial firm energy provider in grids dominated by renewables. Up next is Princeton's novel fuel optimization. A team at Princeton Plasma Physics Lab proposed spin-polarized deuterium-tritium fuel, showing that aligning nucleus spins can improve tritium burn efficiency, reduce fuel needs, and lead to smaller, cheaper reactors. The third study is France's 22-minute plasma record. At France's CEAUS tokamak for the first time, plasma was kept stable for 1,337 seconds, equivalent to 22 minutes, surpassing China's East record. While not yet a commercial device, this is a major milestone for either related tech. Last but not least, the global review from UTP Malaysia. Malaysian researchers at University Technology Petronas reviewed global fusion development and readiness, emphasizing material R&D, international cooperation, and early fusion R&D in Southeast Asia. And that is all for the applications and recent studies on nuclear fusion as a sustainable energy source.
Next, we move to the potential carriers that related to nuclear fusion. First one is engineering. There's a lot of type in engineering field, but the highlighted fields are mechanical, electrical, and nuclear engineering. These are needed because of their skills to design, build, and maintain the fusion reactor. And they are involved in development of advanced materials and systems for fusion power plants. Second is scientists. Scientists in this field of nuclear fusion has two categories, which are plasma physics and also material science. For plasma physics, they need to understand the behavior of plasmas because it is crucial for controlling and sustaining fusion reactors, such as the research and diagnostic of fusion reactors. And for material science, they are needed to testing new materials and withstand the extreme conditions of fusion reactors, such as high temperature and also radiation. Third is about computer and data science, which are computer scientists and data analysts. They have to generate large amount of data from the fusion reactor. After that, analyze and interpret all the data for reactor control and optimization. And the last one is robotics. They usually design and build robots for tasks for the maintenance, inspection, and to repair the fusion reactors. And what about the specific skills needed to them? Let's see together. This is educational background needed, which are strong foundation in science and engineering. Bachelor's degree in physics, engineering, or related field is typically required, and advanced degrees like master's or PhD. Multidisciplinary collaboration is the most important thing to handle the nuclear fusion energy that requires a team of specialists from various disciplines to work together effectively. Other than that is project management. Large-scale fusion projects necessitate strong project management skills to ensure timely completion and efficient resources utilization. Then, problem solving and critical thinking also crucial to keep this energy maintained, such as nuclear engineers must be able to identify, analyze, solve complex problems that related to fusion reactor design and operation. Last but not least, communication and teamwork is the key to make something working smoothly. Effective communication and collaboration are crucial for conveying technical information to diverse audience and working within multidisciplinary. Thus, all of these careers and skills, they give such a big benefits to others. Fusion energy will help to grow green-collar jobs, which are roles that focus on sustainability and environmental impact.
And for the last part is self-development for career in nuclear fusion as sustainable energy sources. The first significance is technological advancement. Nuclear fusion requiring professionals to continuously learn. This allows individuals to stay abreast of this challenge and contribute effectively to the field. Second one is problem solving and innovation. Research are complex and require innovative solutions. The foster problem solving skill and the ability to think creatively. The last one is global collaboration. This involving research and institutions from various countries. This can help individuals effectively collaborate and contribute to international projects. Challenge and strategies in self-development in nuclear fusion. This one, we got high initial cost and long development time. For the challenges, fusion power plants are expected to be extremely expensive to build and require a long time to develop due to the complex technologies involved, such advanced magnets and specialized material. The development needed to optimize reactor design. And our strategy for that is to focus on cost reduction by exploring different reactor design like those that directly produce hydrogen, potentially can make fusion energy more economically attractive. For the second one is international collaboration. Project like ITER demonstrate its sharing and reducing individual country costs. Second one, we got fuel cycle challenge. The tritium extraction and purification is another significant engineering hurdle. The efficient extraction from breather materials is a complex process. Our strategies for that is we can separate by two categories. The first one is fuel injection and the second one is fuel recycling.